Welcome back to Computer Science 4300. Today, we are looking at collision detection and resolution. So we'll figure out what those are in a bit, but essentially how things bang against each other in our video games and all the ways to detect those and the reasons for why we would want to do something like that. Before I get into the lecture, though, I want to provide some motivation for why this is important. So if we see here today, we are doing collision detection and resolution. Then we are going to be doing sprites, textures, and animations. And then we're going to be talking about actions, replays, and components. And the reason for doing those is that we are working up to assignment 3. So let me show you quickly what we will be doing for assignment 3. And here we have a little menu scene. But essentially for assignment 3, we are making a full-fledged platforming game using some characters that may or may not be copyrighted, but this is for educational purposes, right? So here we are jumping around, and you can see that things are colliding with each other. And some interesting things happen when things collide. So bullets collide with things. Here we can see we can destroy a brick. My character is colliding with things. And if we look under the hood here, I can turn on the bounding box drawing and I can turn off the textures, and we can actually see what's happening under the hood here. And under the hood, we essentially just have a bunch of rectangles moving around. And what you actually see doesn't really matter for the game engine, right? We're still going to program the game the same way, no matter what is actually seen. But if I turn back on the textures, right, you can see what's happening here. Or this is what like the player of the game will see. But as the developers, we have the super debug mode. So what we want to do is figure out for assignment 2, at the very least, how to detect that these bounding boxes are going to be colliding with each other. All right, so let's dive into that, shall we? Here we go. So, Computer Science 4300, lecture number 8. We are talking about collision detection and resolution and axis-aligned bounding boxes, or AABB. So collisions in games. Collisions are going to happen basically in any game, and whether or not things actually run into each other, or like explode or things like that, or players take damage, pretty much every game I've ever seen does need to have some sort of collision resolution, like whether or not your mouse is within a specific spot on the screen or things like that have to happen. So collision is very important. Collision programming involves 2 separate stages. They're related, but they're separate. So the first stage is collision detection. So given 2 moving entities with some given shape or bounding box, determine if they intersect. And detection is strictly a geometric problem. So whatever shape these objects are, determine if they're currently intersecting. And then we have the second problem, which is collision resolution. So now that we have 2 entities which have collided, determine what we need to do in order to resolve the physics of the simulation, right? So, and this is going to depend entirely on the game mechanics that you want to implement. So, for example, maybe a bullet is going to collide with a brick and destroy it, but maybe a bullet is going to collide with a pipe and not destroy it. Or maybe a player can move through a cloud, but it can't move through a question block or something like that. So detecting whether or not 2 things are overlapping, that's a geometric problem, and collision resolution sort of involves that geometric problem, but it really depends on what the game mechanics say should happen in order to implement that resolution. So we're going to use some assumptions for these slides so that they fit in with the design and architecture of our course and our game engine so far. So we're going to use the course definition of entity, and if you haven't seen that so far, go back and watch the other lectures. And we're going to assume that the entities have the following components. They're going to have some sort of position component, so they have an X and a Y position. They're going to have a bounding shape component, So whether or not that's like a circle or a rectangle or a line, and they're going to have some velocity component as well. So that's the dx dy is the velocity or change in the xy position on each frame of the game. And so our goal for this lecture is to learn the mathematics and the implementation of that mathematics that allows our entities to actually interact in the game in a meaningful way. All right, so collision detection problems. There's a couple of collision detection problems that we can think about. So the first one is, let's say we have a circle down here and a circle over here, and they're moving, toward each other. Given two entities which have a speed or velocity, position, and bounding shape, determine if and when they're going to collide or intersect. Now, the when part of this and the where part of this is a little bit out of scope for the very simple physics that we'll be implementing in this course. So what we're going to do is the simpler problem of given two entities which have a speed, a position, and a bounding box shape, determine... Oh, sorry. Yeah, this is sort of the continuation of that last slide. This is what I wanted to go to. So given two entities which have a current position, do they intersect? So that is the first part of the collision detection problem that we actually want to work on. So here, for example, we have a blue square and a blue rectangle and a red rectangle. We may want to ask, do those things intersect? And as a human, we can see, okay, these rectangles intersect. But the two circles, they do not intersect. But the green circle and the red rectangle do intersect. So what is the math behind that intersection, and how can we implement it? And not only implement it correctly, but implement it efficiently. The second problem that we're going to want to solve in order to implement the collision resolution in this class is that given two entities which have a current position, what is the overlap position, right? So for example, these two rectangles here, okay, we know they overlap, we know there's an intersection, but what are the dimensions of that intersection? So how would we get this purple area here? How would we figure that out? So I'm sure most of you in the class are intelligent enough by your fourth year that you could probably come up with this formula on your own, but I want to have it in the slides just in case, because it's actually the sort of correct way to implement this isn't obvious, and certainly the efficient way to implement this is not obvious, because it wasn't obvious to me when I went to implement it the first time. So before we start to solve whether or not things are intersecting, we need to talk about their shapes. And in the real world, objects can have completely arbitrary shapes or interaction surfaces. So for example, here I have a glass of water, right? And I have my hand, and they have very different bounding boxes, right? So this glass of water is like, I don't know what you'd call it. I guess it's a conic section where there's a cone, but it's chopped off here and chopped off here. It has like an internalness to it. I can like put my finger inside here and drink from it. My hand is like this arbitrary shape that has these like prolonged things called fingers, and like things can pass through them, right? But modeling this in all of its infinite precision is not going to be possible within a video game. And so these objects are difficult to store, they're difficult to compute, they're difficult to simulate accurately and continuously, and so we're going to have to make some abstractions when it comes to modeling things in the real world in a video game. So it turns out then in computer simulations, our efficient way of modeling things is to sort of break it down into geometry primitives. So all shapes in pretty much all simulations that you've ever seen are made of primitive types. So in 2 dimensions, we're going to have things like lines, triangles, circles, rectangles, right? These 4 basic shapes. In 3D, you might have things like spheres, planes, cylinders, prisms of various dimension, etc. But for this course, we're only interested in 2-dimensional stuff. So the bounding shape concept is going to be, we're going to simulate the interaction bounds of a complex shape with a simpler one. So, for example, if we have here an octagon, right? So we have an octagon shape, or over here, we have the Mega Man shape. So Mega Man is obviously more complex than this octagon. We are going to choose some simpler or the simplest possible geometric shapes, which like sort of intuitively enclose those objects. So here we could approximate this octagon with a circle, right? So anything in our game that interacts with this bounding circle is going to mean that it has interacted with the octagon. Now you can see here that like if we had a really accurate like bullet shot or something that sort of grazed the side here between the circle and the octagon, yes, that is where we have some error, but we've chosen this circle to be sort of like the closest possible primitive shape so that it's good enough. It doesn't need to be like atomically perfect in its bounding box. Over here, similarly, you know, if you've played any NES or Super Nintendo or a lot of video games, especially 2D games, we're going to choose a rectangular bounding box for our player character. And so anything that interacts with this rectangular bounding box is going to be considered as interacting with our player character. And again, of course, we're going to have error cases where maybe a bullet flies by here and it still does interact with the player. So, you know, you might scream like, oh, the bounding box is way off or something, but we will show how we can fix these things a little bit. So 2D bounding shapes, the simplest 2D bounding shape to store and compute is a circle with a given radius. And so we've already covered circle-circle intersection. The simplest possible intersection of two shapes, in my opinion, in 2 dimensions is 2 circles. We already covered that. Other 2D bounding shapes can be constructed with a number of line segments. So the simplest of those is a rectangle or a bounding box. All right. So first of all, we're going to talk about a bounding box size because that really does matter and it may not be as intuitive as it first seems. So most 2-dimensional classic rectangular games are going to use rectangular sprites. So despite what, you know, Mega Man's animation may be doing, we're going to surround it with a bounding box of a particular size. These rectangular images make a natural fit for a rectangular bounding box. Usually, the bounding box will be the smallest rectangle that fits the sprite, so we can use the texture size as the bounding box size. However, that's sometimes not the case. So what do I mean by that? Well, if we look at this, for example, sometimes, or a lot of the time, we're going to construct our textures in a way that they're perfectly rectangular. Right? So we have a brick here, we have a question block here. Like this is obviously the simplest possible case of a really old game where all of our things in the game are almost perfect rectangles. So we get down here, so these are perfect rectangles. This pipe is almost a perfect rectangle. When we start to get into Mario, of course, we have this area here that's not a perfect rectangle, but we're going to try our best to approximate these with bounding boxes that are rectangular. But sometimes the bounding box does not fit the exact bounds of the sprite texture. And so we're going to have to make a custom-sized bounding box in order to fit. So here's what happens internally in the game Mega Man, if you've ever played it. So typically in games, we want to store all of our textures, or in older games, okay? This applies to older games where memory optimization is very, very important. We want to store all of our textures in the same size of image file, okay? So everything, all of our sprites that we want to show in the game, they're going to have the exact same storage size for the texture that displays them. However, if we want there to be like a big range of motion of animation for that type of sprite, then sometimes, like for example here on the left, when Mega Man is just standing still, he's going to have a drastically different size either horizontally or vertically than when they're doing something like jumping. So when Mega Man is jumping, you can see here that the bounding or the pixels that are drawn for Mega Man are much higher and much lower than when he's just standing still. And over here, when Mega Man is running, he occupies much less horizontal area than when he's like in this stage of his animation, or when he's standing still, or when he's jumping, right? So in some cases, they're going to be occupying more space or less space than other times. And so what we do as the game developer is we're going to say, okay, in some cases, Mega Man is not going to be occupying the entire area. Sometimes it's going to be occupying more or less area. So we're going to have to make a bounding box that is not the same size as the texture that's being drawn, okay? So here, for example, in Mega Man, and this is what actually happens in the game, is that when Mega Man is jumping, part of his head will not collide with bullets, and part of his foot will not collide with bullets. However, when he's in the middle of his running animation, if I can draw over here, there may be parts of the side of Mega Man that are not drawn, like over here and over here, that would collide with things, right? Because what we have done is we've separated the bounding box dimensions from the texture that's actually being drawn. And so in assignment 1, what I had you do is there are separate variables for the size of the player and the bounding circle of the player, and that was just to sort of get you used to this, which will be happening in the future. And if we look at an actual example, so this is like a pixel perfect representative example of the original Super Mario Brothers, you can see that pretty much no sprite in the game's bounding box actually matches its texture box. So for example, here we've got the closest one. So Mario is pretty close. Mario, almost all of the pixels, so it matches up exactly with the right-hand side, but not with the left-hand side. And I think that has to do with Mario's running animation. The mushroom, so you could clip a bottom of the mushroom. Mushrooms and beetles are about the same. But look at this. The Koopa is way bigger than the bounding box. And they kind of go from like normal, or normal here, I think, meaning, you know, they're pretty representative of the shape that they're occupying, versus the really weird ones over here on the right. Now, you may have seen in some like speed runs of Super Mario Brothers how they can like jump over the pipe with the piranha plant coming out, and it looks like Mario should have been hit by the piranha plant. And the reason why Mario was not hit by the piranha plant is because Mario's bounding box is like right here when it hits the piranha plant. And if this bounding box is not touching this green area, that green area is actually the bounding box for collisions for the piranha plant. And so if those two things aren't touching, even though the sprites are overlapping, then Mario isn't getting hit by it. And the really weird case over here is the fire that comes out of Bowser. That's just like got such a small hitbox. And so you might see a player like jumping through it at the end of a Mario level, similarly jumping through the hammers that Hammer Brothers and Bowser shoots out. And so that's why. It's because they're not actually touching in the bounding box space, only in the sprite case. Okay. So I talked about briefly in the intro slide axis-aligned bounding boxes. So what the hell are they? So they're also called AABB because of the AABB. So rectangles in a 2D plane can take any orientation, right? Basically, the only definition of a rectangle is that it has 4 sides and the 4 internal angles are all 90 degrees, right? So the definition of a rectangle doesn't mean that it has to be straight. Only the sides have to be perpendicular to each other. So this is still a rectangle. This is still a rectangle. This is still a rectangle. However, detecting intersections of arbitrary rectangles can be a little bit slow. And essentially what you have to do for arbitrary rectangle intersection is essentially check to see, so you take any 2 lines, every pair of lines, and see if they intersect. So you would run an algorithm that's a line intersection algorithm, and we'll do line intersection later, but we're not doing it yet. So you'd have to see, does this line intersect with this line? Okay, no, it doesn't. Does it intersect with this line? No, it doesn't. Does it intersect with this line? No, it doesn't. Does it intersect with this line? No, it doesn't. And so what you essentially have is like an n squared algorithm where n is the number of lines, where every line has to check to see if it interacts with every other line, and that can be a little bit slow. So what game programmers realized was that by aligning our rectangles with the XY axis, we can trade sort of the graphical power of this arbitrary rotated rectangles for much, much faster intersection and collision checks. All right. So if we align all of our bounding boxes with the axis of the XY axis, so we make them perpendicular, so all the sides are straight up or straight across, then we can have really nice intersection and collision checks for those shapes. And so, of course, axis aligned AA, bounding box BB is an AABB. So let's look at some axis aligned bounding box checks. And the simplest possible check that we could do is the very, very first thing is just to check to see if a point, so let's say we have a point here, Px1, so that's point x1 and point x2, is that point within a rectangle? Is it within an axis-aligned bounding box? And how we are going to represent our axis-aligned bounding box for this example is that we're going to have 2 points. So we're going to record the top left point and the bottom left point. So we have x1, y1, that represents the top left, and x2, y2 is going to represent the bottom right. So there are some interesting properties that come with that. Like we always know that x2 is going to be greater than x1, and we always know that y2 is going to be greater than y1, right? Because we've set it up this way. Okay, so let's look at how we can do this. You might think right off the bat that there's some sort of complex like collision checking that you have to do with a point inside, but that's not, it's actually quite simple. So, and remember that we're using 0, 0 as the top left here. So y2 is a greater value than y1 in this case. So point P, which is Px, Py, is going to be inside the rectangle if the first condition is that it's inside the rectangle if the x value of the point, so if Px is greater than x1, but also Px has to be less than x2. So what that means is that Px is between x1, which is the left value of the rectangle, and x2, which is the right value of the rectangle. So if it's between the two vertical sides of the rectangle, then that's the first half. And also, it has to be between the two horizontal sides of the rectangle. So if Py, which is the y coordinate of the point, is greater than y1, and also if Py is less than y2. And that's it. It's just 4 simple checks to see if a point is inside a rectangle. Now, we may also want to use the secondary representation of a rectangle. So the first representation of a rectangle is with 2 points, so the top left and the bottom right. The other representation of a rectangle, which is actually more common in video game representations, is if you have a single point, so xy, and you have a width and a height, right? So you measure it this way. So to get to the bottom right point, it would be x plus w and y plus h. So in this representation, P is inside, well, it's inside, basically, remember, if it's inside the 2 vertical lines. And so the leftmost coordinate is still x, so if px is greater than x, however, now the rightmost coordinate is just x plus w, right? So if px is also less than x plus w. And similarly, like last time, if py is greater than y, so if it's down more than y, but it also has to be less than the bottom line, which is y plus h. So that's it. That is how we detect whether a point px, py is inside an axis-aligned bounding box. All right. So now we move on to the slightly more complicated topic of let's determine if 2 axis-aligned bounding boxes intersect anywhere, okay? So you may think that from my last slide, so, okay, what I can do now is I can test to see if a point lies within a rectangle. So maybe if I can test all the points of one rectangle to be inside the other rectangle, then that's how I could test to see if two rectangles overlap. But that's not the answer. That's actually still too complicated. We can do it better than that. All right. So, axis-aligned bounding boxes. Let's talk about, before we talk about complete overlap, like in this case where like the two are overlapping, what I'm going to do in order to explain the formula we're going to use at the end is I'm going to talk about horizontal overlap and vertical overlap separately. Okay, and that'll help you to like visualize this problem, I think, in a more concrete way. So horizontal overlap occurs if the top of each box is higher than the bottom of the other box. So that means here that like the top of this box is higher than the bottom of this box, okay? And the top of this box is higher than the bottom of this box. So another way of visualizing horizontal overlap is if I can draw a horizontal line that intersects both boxes, then there is horizontal overlap between them. And now if you go Google horizontal overlap, you may not, this is a term that I've sort of come up with for teaching this course. So you may not see this in a textbook, you may not see it on Google. Okay, so the way we just said it is that if the top of each box or rectangle, I'm going to use box and rectangle interchangeably, if the top of each box is higher than the bottom of the other box, then we say there's horizontal overlap. So how would we phrase that mathematically? Well, it's pretty easy actually, and here's the formula. So y1 is the top coordinate of box 1, and y2 plus h2 is the bottom coordinate of the other one. So to see if the green rectangle, its top, is above the bottom of the red rectangle, we just have to check to see if y1 is less than y2 plus h2, right? Because here's y2 plus h2, it's the bottom over here, and here's y1 up here. And then if we reverse those, also very similar. So if y2 is less than y1 plus h1. So those are the two checks to see if there's horizontal overlap. The opposite of that is vertical overlap, okay? So vertical overlap occurs if the left of each box is less than the right of the other box. So let's have a look at that. And so there's vertical overlap. We can, this comes straight from the last slide. It's just doing it in the X direction instead of the Y direction. So if the left of this box is less than the right of this box, and the left of this box is less than the right of this box. So if x1 is less than x2 plus w2, right? So we get the right-hand side by adding the width to the left-hand side. So if x1 is less than x2 plus w2, that means this left is less than this right. And if x2, okay, so this one, now we want to check to see if it's less than this one. So that's x2 less than x1 plus w1. All right, so now that we know what horizontal and vertical overlap are, who can tell me how to check to see if two boxes intersect? I'll take a minute to see if anyone in the chat can tell me now, based on what we know about horizontal overlap and vertical overlap, how could I detect if they're actually one is sort of like within the other, or if they're overlapping? All right, perfect. Someone answered correctly. Yep, so there's lots of correct answers out there now. So the correct answer is there's an intersection if both objects overlap horizontally and vertically. So if we have horizontal overlap, again, that means I can draw a line between them, a horizontal line between them that goes through both. And if there's a vertical overlap, I can draw this is not a very vertical line, but I'm using a mouse. So I can draw a vertical line that goes between both of them. So that means that axis-aligned bounding boxes intersect if those 4 conditions are met. So this is the condition for vertical overlap, and this is the condition for horizontal overlap. And so you can tell now that this is like a pretty simple calculation, right? We don't have to go through and do all possible like 16 line detections and all this kind of stuff. All we have to do is just make this really simple observation of is there a horizontal overlap and is there a vertical overlap? So that tells us if 2 axis-aligned bounding boxes intersect, but it doesn't tell us by how much they intersect, okay? All right, so in our game, so far, I've been in the slides, I've been using the top left as the XY coordinate of the rectangular object. Now, that is going to have benefits and drawbacks in very specific situations. So, in our game, in order to make certain calculations a little bit easier, just adjusting my camera here, we are actually going to use the center position of the entity for the position of the axis-aligned bounding box, okay? And this is going to make some things really easy in our game, much easier than if we had used the top left coordinates. So how do we calculate the overlapping area for a centered, positioned, axis-aligned bounding box? Okay, so in our game, so here's our thing right here. We're going to have a position XY, and that represents the center of the object's X and Y position. And we're going to have a width, and we're going to have a height. In our actual game engine, in terms of the actual components that store this, we're going to have a transform component, and we're going to have a bounding box component, okay? So the transform component is going to have a number of pieces of data here, and one of them is the position. So that position that we have in our C transform, that is going to be position XY. So pos.x and pos.y, that is the center of our object. The previous position, that is going to be, it's going to store, again, it's the center of the object, but we're going to store the position that the object was in on the previous frame. And we're going to use that little bit of data to help us resolve the collisions in a correct way. So we need to know the current position in order to see whether or not there's currently an overlap. But if we also store the previous position, that's going to allow us to do things like tell if the object was coming from the right or from the left. And so we can resolve things that way. It's also going to contain a scale, and we don't need to use the scale for these calculations. And it's also going to contain a speed. Actually, that should actually say velocity because it's a speed vector in the X and Y position. And then an angle, but we're not going to use the angle for this particular calculation. We're also going to have another component, which is the bounding box component. And the bounding box component is going to measure the width and the height of the bounding box. So the bounding box X, oh sorry, let me move this camera here. So the X component of the bounding box, so the size, so bounding box size.x, that's the width of the bounding box, and the Y is the height of the bounding box. So that's what that means. And then we're also going to have this half size value, and that's just the size divided by 2. And so the half size is going to come in handy for us when we do our calculations, because it's going to tell us essentially the distance from the center to the edges. And we'll see why the half size comes in handy, but it's pretty worth it to just store this half size calculation rather than divide things by 2 every single time we want to use that half size box. So that's what that is. Okie doke. So let's move on. So here we have two of our AABBs, and using this this representation that we're going to be using in the slides of x1 and y1 being in the middle, how are we going to actually compute whether or not they overlap? So the formula changes a little bit. First, what we're going to do is we're going to compute dx. So dx you can think of as a difference in x or a distance of x, okay? And so that is going to be between the centers of the two rectangles. So the distance in the x direction, or the difference in the x direction, is going to be the absolute value of x2 minus x1. Because this second rectangle might be on the left, it might be on the right, and so we have to take the absolute value here because we're not sure right now which of x2 or x1 is the greater of the two values. So here we have dx. Next, what we're going to do is we're going to calculate, or we've already stored, half of the widths of both of these rectangles. Okay, so we've got W1 over 2 here, which is this green line segment, and W2 over 2 over here, which is this red line segment. So this is the data that we have right now. And we're going to see that there would be an overlap in this direction, essentially, if these two line segments overlapped, right? So here, there would be no intersection. But here, there would be an intersection because they're longer. So the calculation here just basically says if dx is longer than the sum of this value and this value, then there's no overlap, okay? So there's an overlap in the x direction if W2 over 2 plus W1 over 2 minus dx. Now, if that's positive, then there's an x overlap, okay? So if the sum of the green and red is greater than the black, then that means there's an overlap. And I hope you can see that by now. And this is why we want to store W2 over 2 and W1 over 2 as that half size, because that's going to save a lot of calculations for us later. Alrighty. So let's do the exact same thing now, except vertically instead of horizontally. So we're going to take the difference in y, so that's dy, and that's the absolute value of y2 minus y1. And again, I've got my camera over that, so I'll move it. And let's see here. We're going to store and pre-compute the half heights, right? So h1 over 2 and h2 over 2. And similarly, here there would be no overlap, but if the sum of those two half heights were bigger than dy, then we would have an overlap. So if we have the sum of the half heights and we minus dy, then that's positive if there's a y overlap, okay? So if we put all of that together now in one slide, and we move this back up here, then we have the following. So we're going to have our delta value, okay? So delta is essentially going to be a vector, so it's going to be a vec2 in our code. And that's going to store the difference in the x here in the first component and the difference in the y in the second component or the second index. So now if we have something that overlaps, we want this ox value and we want this oy value, right? So that's the overlap x and the overlap y. So overlap x is just going to be equal to width 1 over 2. This is the formulas we said before, which is half the width plus half the height in half the width plus half the height minus the delta x. And the overlap in the y direction is half the height plus half the height minus the difference in the y direction. So now we have overlap, and that our overlap vector is going to be this ox and this oy. And we're going to say if both ox and oy are positive, then our shapes are overlapping. And if for some reason we want to know by how much they're overlapping, then those two values are stored inside this right here. Okay, so we've simplified our calculation even more than the 4 if statements we were doing before. So before we had these 4 if statements here. See that? Now all we have is this right here, and it gives us more information. So we do all of these So it turns out that it's way faster to do addition and subtraction than it is to do if statements. So all we have to do is calculate these values, and then we have essentially one if statement, which says if OX and OY are positive, then we have an overlap of our two things. All right. So now let's talk about resolving collisions. So now that we've detected the AABB collision, what do we do now, right? We have the value of OX and OY, but how do we actually use them? So the resolution of the physics or the collisions is going to depend entirely on the physics and the mechanics of what our world should do. So for example, one of the most popular things that we want to do in a video game is that if the player collides with a world geometry tile, then we don't want there to be any overlap, right? We want the player to kind of be pushed out of the tile. So here's an example here. And what we're going to do is this object is going to have some movement to the left. So let's say that this is the player, for example, right? The player wants to move to the left, and they're going to have some amount of distance traveled on every frame, right? So this sort of, this is their velocity in the x direction. This is their v.x. Right here is this little amount. So this is frame 1 of the game. And then I'm going to step through here. This is frame 2, frame 3, frame 4. Okay, see how that works? So I'm going to step through. At some point here, I'm at this position. Based on my velocity, I update. I'm at a new position. Then I'm at a new position and a new position. And then, okay, now something interesting has happened. I keep moving to the left. I keep moving through space until the point where I have a collision. So the collision has been detected at this point. So I'm going to have some code in my game engine that says, I'm constantly checking to see if the player is overlapping with any of the tiles in the game. And so now I've detected that, right? So what we want to do in order to resolve this collision is resolve this collision by pushing the player back out by an amount equal to the x component of the overlap, right? So see how that works? So I've gone left, 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 left. Oh, there's an overlap. No, push that guy back out, okay? So at some point, for a split second in our game engine, we're going to detect the overlap, but then before we render the next frame, we're going to resolve the collision by pushing the player back out of the wall. All right? And then what's going to happen is if we keep holding left, for example, on the very next frame, there's going to be overlap again. But still, on that frame of calculation, we push the player back out, and that's how we resolve the collision, and then we render the next frame. Then on the next frame, we're still going left, we push it back out. And so all the player ever sees, the player never sees that this thing has overlapped with the tile. Because what the player sees is this. Here's frame 1. So there's no overlap. We just render it. Then no overlap, render it. No overlap, render it. No overlap, render it. Overlap. So we detect the overlap, and still down here, see it says frame 5 of the game. Still on frame 5, we push it back out, and then we render it. So this is all the player ever sees, and it just hides that fact from the player of the game. Then it goes in again and out again, render, in again and out again, render. So we've hidden the collisions or the overlap from the player. Now, some game engines don't do this very well, especially in 3-dimensional games, because this problem is a little bit harder. It's a lot harder in 3 dimensions. Hence why we're not writing a 3D physics engine in an undergraduate course. But we do try and hide that process from the player as much as possible. So here is a tricky case, all right? Here's a tricky case. So we've detected, this was an easy case to resolve because we detected that there was overlap, there was vertical overlap, right? But we saw that all of the overlap was in the x direction, so we can just push the player back out. But here's a tricky case. let's say the player is moving like this, like this, like this, and now what do we do? Well, before, all we did was we calculated the overlap here, and then we moved the player by that overlap. But here the overlap is actually diagonal, right? It has an X and a Y component, whereas before it only had an X component. So in case 1 here, would we push it back out like this? Right? Would we push it on top? Maybe. Maybe we push it back out to the right. It completely depends on your game engine. So for example, in some games, they might push you up to the top. Like if this was Mario running towards some stairs, it might say, okay, push him onto the top of the stair. But if we look here, resolving this by pushing back out by the overlap, that looks a bit weird to sort of just push it back out so the corners are touching, right? So what do we do here? We have some options, right? So what might those options be? Well, okay, so this slide just means that in one case, we may want to push it up. In another case, we may want to push it up right. However, maybe what we wanted, so this is what that would look like, okay? So here, maybe you want to go left, 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 and then push it up, right? But maybe we want to go left, 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 and just keep it here, right? We want to push it out to the right. So it depends on that. So there are options, right? And that depends on your game mechanics. So when detecting collisions in our game, they will happen at some specific frame, right? Like I'm on frame F of the game and this collision has happened. On the frame before the collision is detected, there is no collision, right? And I know that sounds weird to say that, but essentially means that like on one frame there was no collision, and on another frame there was a collision. And so what I mean by that is on one frame everything is okay, and on the next frame everything is not okay. We need to resolve things somehow. So we could maybe try to use overlap to detect which direction the movement came from. So what we could do somehow is, for example, let's just look at this overlap. So if this is all the information that we have right here, how would you resolve this collision? Well, for example, you may say, okay, maybe the X overlap is less than the Y overlap, so push this thing out by an amount equal to the X overlap, right? But the problem there is that maybe the object actually came on the previous frame was above it. So maybe we would want to push this out in the Y direction so that the two blocks were kind of like this, and one came down and just stays there rather than sliding off to the side, right? So it could have come from the Y direction, or it could have come from the X direction. So it's kind of a tricky case. Like if all we have is this information, we don't really know what to do. And so someone in the chat out there said, maybe we could use the velocity vector to determine which side that it actually came from. And that's a good idea. What we have done though in our game engine is simplify that a little bit by using the previous position, okay, to detect the direction. So the previous position can be used to detect the previous frame's overlap. And this is something that I've found that works really well in practice. And there may be simpler solutions out there, but I've found this sort of a good mix of speed of implementation, understandability, and quality of results. So this means that if the previous frame's overlaps Y value is greater than 0, then the movement came from the side. Okay? So that means that resolving, if the previous frame's overlaps Y is greater than 0, then we're going to resolve collisions by pushing in the X direction. So that means if there was a horizontal overlap on the previous frame, and then on like a current frame, there's an overlap. So this is what's going to happen. So this means that it's coming from the left, or it's the previous frame's overlap is going to have a y value greater than 0. Then this happens. We're going to look at the previous overlap, and if it had this property, then what we're going to do is we're going to push it out to the right. So that is going to happen. So what we're doing is we're basically simulating the forces of two actual blocks moving together, where I don't have two blocks that I can use here. Oh, here we go. I have a charger and I have a phone. So if these two are coming together like this and then they meet, they're going to be blocked, right? Like this. So that's what we're doing. We're simulating here. Similarly, if one comes from the top, we don't want them to slide off like this. We want them to actually be blocked. Okay, now that actually, it kind of ends up being a little bit funny in a way, because we could have like Mario sitting by his toe at the end of a ledge. Let me show you what I mean by this. So let me go real quick over here. So let me play some Mario here. And what it's saying is that, perfect. So Mario or Mega Man here, like, if he comes from this way, he's going to be blocked by this. So if I look at the bounding boxes, right, this means that the bounding box coming from the top is going to be pushed back up instead of pushed to the side. And going to the right, it's going to be stopped here instead of going to the left, right? Or so instead of going up. And what we see is that in situations like this, it does look kind of funny, where, you know, Mega Man here can actually be just like defying gravity by having a toe holding him up. But that's sort of, you know, we trade a little bit of realism for easy to compute graphics. Sorry, easy to compute physics. Okay. And similarly, if there was, oh, let me go back to the slide view here. If the previous frames overlap had an x component greater than 0, then that means that the movement came from the top or the bottom. So if we're coming from the top here and we see this happen, then we're going to push it upwards. And that's going to sort of have the best case, okay? So the edge case here is that, oh yeah, no edge case yet. Sorry for confusing you. So the summary is that a collision came from the top if it has a previous overlap's x value greater than 0, right? Because it's overlapping in the x direction like this. And its y is higher. A collision came from the bottom if its previous overlap had an x greater than 0 and its y value is lower. So not only do we want to know if it was a coming from the top or bottom, but we might want to specifically know if it came from the top or specifically if it came from the bottom. And why would we want to know that? Well, again, let me just show you the example from the game here. And the example from the game is as follows. If I fall onto the top of a question mark block, nothing happens. But if I collide from the bottom of a question mark block, I want the coin to appear, right? And then it deactivates this block. So that is the use case here, where we may want to like stomp on a Goomba from the top, but not be able to stomp on a Goomba from below. Okie doke. Let's go back to the PowerPoint. Okie doke. Here's the tricky case. Here's the edge case that I wanted to say a minute ago. What if the previous frame had no overlap in the x direction or in the y direction? So here, for example, if we're coming from a diagonal and we have no overlap on one frame and then both overlap on the other frame. So in this case, you can't use one or the other, and you must just decide on how to resolve collisions based on the previous overlap or overlap size, okay? So maybe you say, okay, maybe if it was coming more from the top than from the bottom, maybe you do something, or maybe you just put a priority on it and say something like, well, if neither overlapped on the previous frame, I'm always going to push it out to the side rather than to the top or the bottom. So you just have to make that decision, etc. Also, what if an entity overlaps with multiple entities. So what if we have, like in our Mario game, we have a bunch of entities stacked on top of each other, and we're moving, and then what do we do here? It overlaps with multiple entities, right? So it can be tricky, and it can depend on the order of collision checks. So if we've maybe this block had some physical properties that were different than this block. And so maybe if this was if this was bouncy, but this wasn't bouncy, right? If we checked with this first, maybe it'll bounce. But if we checked with this first, maybe it wouldn't bounce. So we have to be careful with these cases, because the order of resolving collisions does matter. And so the previous overlap method, it usually resolves this case, but using the previous position only doesn't, okay? So make sure that you're making use of this previous overlap, because it can help you here. And typically what happens is that you're going to do collision resolution, and let's say you do it on this one first, it's going to push it out, and then usually your stack are all aligned, so it doesn't really end up mattering that much. So that's just what you would do in a case like this. And ideally, in a case like this, it's going to resolve itself. But what you may find sometimes, if I can back up here a little bit, is that sometimes, and this might happen early on in your debugging testing, is that you get this square right here. Let's say it's coming over here from the left. It might actually get stuck right here. Because what's happened is your entity was falling like this, and it fell so that it was overlapping both of these tiles. And what you did was you pushed it up, and then it's kind of resting here. And this is common. It's not too difficult to resolve, but this case is actually how some bugs in popular video games are found, where you're colliding with the edges of one bounding box, but not the other bounding box, and it pushes you in weird ways. And this can happen in Super Mario Brothers and in Mega Man and in lots of other games. So don't be surprised if it happens to you, but I have faith that you can figure out how to solve it. So just an important note is that all the collision resolution that we discussed here is for the simple case of just avoiding overlap. It's useful for things like walking on tiles. So as we're walking on tiles, we want to move along. Not being able to pass through tiles, bullets hit tiles, etc. There are many other kinds of collision resolution though. So there's kinematic, object, elastic, or inelastic collisions where things could bounce. There's physics simulators with mass and forces. We're obviously not going to get into all of that stuff in this course. This is not a physics simulator course. This is let's make some simple games. It's mostly a programming architecture course. So I don't want to get bogged down with trying to write a full simulator. Typically, what's going to actually happen is if you want to use a full physics simulator in your game, what you'll do is you'll use a library for that, right? So you'll download something like Box2D, and that's available for C++. It's available for JavaScript. I think it's available for Java. I'm not sure. But you would just download Box2D, and you would let it just take care of all your movement stuff, right? And you wouldn't have to think about it. But that's not very fun. We want to do our own collisions in this course. So just note that we're doing the simplest form of collisions that let us make fun games, and we're not going to be making Half-Life 2 or these games with full physics things. Just a little side note here is that Super Mario Brothers collisions operate differently than we presented. Just consider the case of Mario jumping on top of an entity, right? So if Mario jumps on top of an enemy, how did they actually determine that rather than from below? So what they did was they used a similar form of axis-aligned bounding box to see if they overlap, right? So there's two things. There's Mario, and there's an enemy, right? So here's the bounding boxes, and at some point they're going to overlap by a little bit. But what Super Mario Brothers does is it checks to see, is Mario's y velocity positive, right? So is Mario falling? Well, I guess you could say that's negative. So if Mario is currently moving downward, then the entity dies. That's it. So over here, for example, Mario is physically below this Goomba. So if Mario is on the way down, even though Mario is below the Goomba and colliding from the side, right? So this collision is obviously from the side, not from the top. However, all Super Mario Bros. 1 does is check to see if the velocity.y is negative in value, right? So if Mario is falling, it kills the thing, no matter where they are overlapping. Even if it's just a tiny sliver down here in the bottom left, that's all that matters. And similarly, no matter where they collide, if Mario is moving upward, Mario will die. Right? So it's just interesting how they did it, because it's a very, very simple collision check. And you know what? You may want this sort of thing in your game, right? You do not have to do what we did in our game, because what we're doing in our game is this sort of physical box-to-box, cannot pass through each other sort of thing. But if you want something that plays more like Super Mario Brothers, then you could implement what they have. But for this course and for assignment 3, we're going to implement what I told you, right? Because I want everyone to implement the same thing. Now, there's a few videos here that I highly recommend watching. And please, please watch, I would say, these 2 videos. This one is a little bit longer than this one. This video, if you've never seen Pan and Coke before, absolutely incredible. He has done like multiple PhD work worth of stuff in Super Mario 64. And in that video, he explains how the programmers programmed the movement and the floor, the walls, and the ceiling collisions into Super Mario 64. And it is so brilliantly simple that it blew my mind, and I hope it blows your mind too. And in this video, Bismuth does an excellent job of explaining all the glitches that happen in the Super Mario Bros. 1 speedrun. So like, how do people clip through the walls, right? And it's just an absolutely amazing video, and I would actually play it in class, but I want to minimize the amount of freebooting that I do. Just go watch those videos. And for those of you in the chat, I am going to paste those videos as soon as I stop the recording of the lecture. So, but for those of you in the class, please go visit these videos, and I would recommend watching all of them because they're just really incredible video quality. So that is the collision detection and resolution for axis-aligned bounding boxes. And I hope you found that a little bit informative. And I know that most of you are not even going to open this until it comes time to, implement your assignment 3. But, that's the joy of online classes. And next class, we will show you how to make your 2D games a little bit prettier by adding sprites, textures, and animations. So just quickly, for example here, like how did we make Mega Man animate while running? How did we make this explosion happen right here? And how did we make like the coin animate and stuff like that? So all these sorts of things, and it'll turn out it's actually pretty easy. But it's easy within the ECS framework. Just give me 1 second. Oh, my cat just came in. He doesn't want to be picked up, though. I was going to show you my cat. All right, so that's it for today's lecture, and I will see you on Thursday for the next one.